What's up, Tumnad lectures? In this video, we are looking on what we call the ECG. If you find this video helpful at the end of it all, please make sure you like the video, comment down in the comment section, and please subscribe. Let's go ahead and get started. So now in this video, we are going to be looking on the detailed part of what we call the ECG. In the previous video, we looked on what we call the basic components of what we call of the normal ECG, but we did explain how those kind of the patterns, how they were coming about. In this video, we are going to go into an extra mile and explain how all those kind of the waves on the normal ECG, how they come about. But before we go into the detail of that, we need to first understand some of the basic terminologies during the study of what we call the ECG. If we are to master the interpretation of the ECG, we need to first know some of these common terminologies. What are these terminologies? We need to first understand what is depolarization. We need to understand what is repolarization. We need to first understand what is a lead. We need to first understand what is electrode, and we also need to understand what is a vector. Okay, those are the basic information that we need to first understand before we go very far into the detailed part of what we call the ECG. In this video, we are going to be looking on what we call the depolarization of the contractile cell of what we call of the myocardium. Now, we have extracted only one cell on the contractile myocardium. We want to see how this cell is going to be getting depolarized. That's going to be the main reason in today's video. Let's go ahead and get started. So now this one is going to be a cell. It's going to be part of what we call a contractile cell. And of course, there is also another cell which is going to be starting from here, going the other side. We want to see how this kind of the depolarization from this cell is also going to be leading to the depolarization of the next cell. Because that's how depolarization of one cell leads to the depolarization of another cell through some kind of the proteins, which is we'll talk about, which is going to be allowing the movement of different kind of cations. Okay. Now this cell, let us first pretend that this cell is at rest. And whenever a cell is at rest, like for example, this cell is going to be electronegative inside this cell. Now it means this cell is going to be having what we call resting membrane potential. Okay, we call resting membrane potential. Now, what is resting membrane potential? Resting membrane potential is that voltage difference between inside of the cell and then outside of the cell. And that's why we have said this cell, when it is at rest, it is going to be electronegative intracellularly. Okay? Now, the resting membrane potential for the case of this cell is going to be approximately around negative 90 millivolts. Let's first pretend for a minute that it is going to be negative 90 millivolts. Okay, negative 90 millivolts. Now, this cell is at rest and is having too much of electronegativity inside this cell. And we're going to be having a lot of the potassium ions inside this cell, and we shall have a lot of sodium ions which are going to be extracellular. Now, what is going to be happening is that let us now first stimulate this cell. We're going to stimulate this cell, and when we stimulate this cell, we're going to be now having some little bit of what we call entry of cations. Okay, so now let's first stimulate this cell. We are going to be stimulating. We're going to be stimulating this cell. Now, when we stimulate this cell, we're going to be starting to see some cations little bit trying to enter this kind of the cell. Okay, so now you're going to be having entry of what we call cations. Preferably, we're going to be having entry of what we call sodium. Okay, we're going to be having entry of what we call sodium. Now, if we have entry of sodium ions inside this cell, it means the negative polarity of the cell inside is going to be reducing. That means this cell is starting to become electropositive slowly by slowly. Okay, now this entry of sodium ions is going to move the membrane potential from resting membrane potential up to around the threshold potential. Okay, is going to be moving this membrane potential, and then it moves it towards threshold. Okay, so now let's first pretend that this one here is going to be now our threshold potential. And then for the case of this one, let's first pretend that the threshold potential is going to be maybe around negative 70 millivolts. Now, what is very much special is that whenever this membrane potential reaches threshold, we have those kind of the channels that are waiting for the membrane potential to reach threshold. What are these channels? You see these channels here. These channels here are very much special. These channels are what we call voltage gated sodium channels. Okay, these channels here are what we call voltage gated sodium channels. For them, they open only when the membrane potential reaches what we call threshold. Now, what happens is that when this kind of the voltage gated sodium channels, when they open, sodium is going to be starting to rush inside at a very high speed. So now we have now entry of sodium at a very high speed. Now, the too much entry of the sodium ions by the opening of the voltage gated sodium channels is going to be increasing the electropositivity inside this cell. It is going to be moving this kind of the membrane potential. It will move the membrane potential up to around, for example, up to now, for example, this is going to be 0 millivolts. It means that as it reaches 0 millivolts, it means that the whole of inside the cell, it is neither positive nor negative. Okay, it has now washed away all the electronegativity inside this cell. It means there is no positive ions, there is no negative ions. These sodium ions that came in, they were cancelling out the electronegativity. But this entry of the sodium ions will further make the inside of this cell to become now electropositive. Okay, so now let's say, for example, up to around positive 10 millivolts. Meaning that at this time, the inside of the cell is now electropositive. Okay, inside the cell now it is electropositive. We have washed away all the electronegativity inside the cell. Now, whenever this cell becomes electropositive, we have washed away the electronegativity, which is naturally inside. We say that this cell is depolarized. Okay, that is now a beautiful term. We say that this cell is now depolarized. Now, when this cell becomes depolarized, we have those kind of the specific type of the channels that are super sensitive to what we call depolarization. Now, what happens is that you see these channels here, they are sensitive to what we call depolarization. Whenever this cell becomes depolarized, that's when these kind of the channels are going to be opening. What are these channels? These channels here, this one here is what we call voltage gated potassium channel. This channel is going to start opening. Okay, it's going to start opening, and once it opens, you're going to be having now potassium ions starting to leak out. Now, what is the significance of this? Whenever potassium leaves the cell, this cell is going to be starting to get back into its electronegativity slowly by slowly, depending on how fast potassium is going to be effluxing or is going to be moving out. Now, as voltage gated potassium channels are opening, it means now we are trying to pull back at the membrane potential back to its what we call its electronegativity. This is what's going to be happening. So now, for a brief moment, you're going to be having a slight kind of the movement back to the membrane potential to around 0 millivolts. Now, what's going to be happening? These voltage gated potassium channels, they are now also going to be telling that also these channels here also slightly a bit open. What are these channels here? These channels here are voltage gated calcium channels. Okay, are voltage gated calcium channels. Now, when these channels open, they are going to be allowing entry of what we call calcium ions. Now, what is very funny at this moment is that the entry of calcium ions and exit of the potassium ions, they are going to be now at this time moving almost at the same rate. What do I mean by this? If there are 2 potassium ions moving out, there are also going to be 2 calcium ions coming in. Meaning that at this point, there is going to be no change in membrane potential. And this one is going to be creating what we call a plateau. Okay, it's going to be creating what we call a plateau. Okay. Now, what's going to be happening now, these calcium channels, these voltage gated calcium channels, they are also going to be opening for a very brief moment, and then they are going to be now closing. Okay, they are now going to be closing, and once they close, we shall have now an extensive amount of voltage gated potassium channels opening. You see these channels here, they are now voltage gated potassium channels, meaning that you're going to be having now an extensive efflux, of what we call potassium. Meaning that if we have an extensive efflux of what we call potassium ions, we are now starting to regain our electronegativity inside the cell. What do I mean by this now? This electropositivity is now also starting to get disappeared. Okay, we are now getting back to our electronegativity, but we have not yet washed all what we call the electropositivity. Now, as more of the potassium keeps leaking out, we are going to be now bringing back our membrane potential. It's going to be coming back to what we call to the resting membrane potential. Okay, so now our membrane potential has now come back finally to what we call to our resting membrane potential, and we said whenever a cell is at rest, it's going to be electronegative intracellularly, meaning that all our electropositivity has now been completely washed away. Okay, we have now regained our electronegativity. Okay, so now whenever we gain back our electronegativity of the cell, we say the cell is repolarized. Okay, meaning that this is going to be a phase of repolarization, and this one here is going to be a phase of depolarization. Okay, it is such another a beautiful thing. So that if you have a wave of depolarization followed by a wave of repolarization, these two waves together is what we call the reaction potential. Okay, if you have what we call dipolar, if you have what we call depolarization, if you have what we call depolarization, followed by repolarization, okay? These two common terminologies together, they form what we call action, potential. Okay, what we call action potential. So now action potential is going to be a wave of depolarization followed by what we call repolarization. Okay. Now, something else which is so much beautiful is that how is this depolarization going to lead into the depolarization of another cell? There's going to be another cell here. And now, during that time when we are having a lot of the cations, before the polarization phase, some of the cations, they start now moving and then they enter into another cell. The question is, they enter into another cell, passing where? We have these beautiful these proteins. These proteins here are what we call the gap junctions. Now, these cations are going to be entering into another cell. Now, if they enter into another cell, if that cell was at rest, for example, on resting membrane potential of around negative 90 millivolts, if we have some of the cations trying to tickle inside there, it means its resting membrane potential is also going to be starting to move towards the threshold. And once reach a threshold, by the entry of these cations from this cell, which is already depolarized, this means that voltage-gated sodium channels are going to be opening. And once they open, a lot of the sodium is going to be rushing in, which will move the membrane potential into what we call around positive 10. And by that time, we say that also the next cell is fully depolarized. And of course, the proceeding processes is going to be the voltage-gated potassium channels, which are depolarization sensitive, are also going to be opening for a brief moment, with also opening of what we call the calcium channels. Okay, this will create this kind of small depression, and of course, we have what we call this kind of the plateau, whereby the calcium ions entering in and the potassium ions leaking out are also going to be on equal interval. And then finally, the voltage-gated calcium channels will close, which allow too much of the potassium ions to be leaking out, bringing back the membrane potential back to the resting membrane potential. So now this kind of the process is going to be happening on the next cell and the next cell and the next cell and the next cell until the entire myocardium gets depolarized. Okay, so now that's how generally how depolarization is going to be coming about. Okay, now that we have seen what is depolarization, what is the repolarization, let's have just a very quick break. Then immediately after the break, we are going to go ahead and see what is a lead, what is electrode, and what is a vector. We meet immediately after the break. Welcome back from the break. In this session, we are going to be looking on what we call the principles of the galvanometer, because our ECG works on the principles of what we call the galvanometer. But before you go to what we call the galvanometer, I want to take you through on what we call the basics of what we call of this diagrammatic illustration. So now we have just brought a very small kind of the tissue from what we call the myocardium. This is going to be tissue A, this is going to be tissue B, and this one is going to be tissue 3. Now, we are connecting electrodes on both sides. Now, what is electrode? Electrode is going to be that electrical device which can be put on the skin, and it detects the electrical current generated by the heart. You know, whenever the heart generates electrical activities, this electrical current can move throughout the body, and these kind of electrodes can pick this kind of the current direct from the skin. These electrodes can be a positive electrode and it can be a negative electrode, of which they're going to be having these wires that are going to be taking the kind of the information to this kind of the machine which we call the galvanometer. Okay, so now we want to see how is the galvanometer going to be deflecting if this tissue is stimulated from different areas. Okay, that is going to be the main reason of this session. Let's go ahead and get started. So now let's first pretend for a minute that we are going to be stimulating this kind of the tissue from this area. At this time, it is at rest. And whenever this tissue is at rest, it is going to be electrically negative. Okay, this tissue is going to be electrically negative. All of these cells are going to be electrically negative. Now, if we stimulate this tissue from this area, of course, when the cells become stimulated, sodium is going to start entering into that cell. And if sodium enters that cell, the membrane potential of that cell is going to be changing from resting membrane potential, and it reaches around the threshold. When it reaches around the threshold, voltage gated sodium channels are going to be opening, and a lot of the sodium is going to be rushing in. And this one is going to be leading on that cells to become electrically positive. Okay, so now that one is what we call depolarization. So now this cell here is going to become depolarized. And once it becomes depolarized, through the gap junction, some of the cations are going to be moving to the neighboring kind of the cells, leading to the depolarization also on those cells. So even also, these cells are also going to get depolarized. Even also, these ones are also going to get depolarized. So now, during this kind of depolarization, a lot of electromagnetic force is going to be generated. So now, until the whole tissue becomes depolarized. So now, the depolarization was moving from the tissue point P up to point Q. Now, the electromagnetic force which was generated here can be illustrated using the vectors. A vector is going to be a one showing the direction of the depolarization or even repolarization. So now, if the depolarization is moving from point P to point Q, our vector is going to be pointing the other side. Okay, this is going to be now our vector. But this vector was for the case of the depolarization, and depolarization is going to be by the movement of what we call the positive charges. Okay, now that we have seen what vector means, let's go ahead and see how is this galvanometer going to be behaving. Okay, where is our pointer going to be deflecting? Is it going to be deflecting to the positive side, or it's going to be deflecting to the negative side? So now this side here is going to be now for example, our positive side, and then this side here is going to be now our negative side. Now, what does the principle of the galvanometer say? If the depolarization is moving from the negative electrode and it is moving towards a positive electrode, our pointer is going to be moving towards the positive side. Okay, so now our pointer is going to be now moving to to the positive side, and this one is going to be giving us a positive deflection. Okay, so now how does the ECG give us a positive deflection? This one here is going to be our positive deflection. Okay, so now this one is what we call a positive. This is what we call a positive deflection. Okay, this is what we call a positive deflection. Now, it means a positive deflection is going to be moving up. Now, whenever the whole of this tissue becomes fully depolarized, shall we again have electromagnetic force being generated? No. It means that's the only time when our pointer is going to be coming back to the neutral. Okay, and it's going to be producing an isoelectric line. An isoelectric line is going to be this line which is going to be moving, showing that either the whole tissue is fully depolarized or even the electrical current is being held somewhere within what we call the myocardium. So now that was for the case of experiment on tissue A. When we come on experiment with the tissue B, the other tissue, we stimulated it from this side. Now, this time around, you're going to be stimulating it from the other opposite side, the Q side. Now, this tissue at this time is still at rest, okay? And whenever it is at rest, it is going to be electrically negative intracellularly. Now, if we stimulate this kind of the tissue from this side, sodium is going to start entering these cells. And when the sodium enters these cells, the membrane potential is going to be moving and moving until it reaches what you call threshold. When it reaches threshold, voltage-gated sodium channels are going to be opening and a lot of the sodium is going to rush in. And when sodium rushes in, the electronegativity of the cell is going to be washed away. And we say that these cells is becoming depolarized. Okay? So now this time around, the depolarization is going to be coming from these cells. Of course, the depolarization of these cells will lead the depolarization of the neighboring cells. So even these cells also becomes depolarized. So now the depolarization is now going to be moving throughout the entire kind of the tissue. Now, you realize that now the depolarization is moving from point Q going to point P. So now, how is it going to be now our vector? Now, our vector is going to be facing this side. Okay, our vector is going to be facing this side, and still our vector is going to be still carrying a positive charge because the depolarization is starting from point Q coming back to what we call to point P. Now, what does the principle of the galvanometer say? Whenever the depolarization is moving away from the positive electrode towards a negative electrode, our pointer is going to be moving to the negative side. Okay, so now this one is going to be our negative side, and then the other side is going to be now our positive side. Now our pointer is going to be moving towards a negative side. So now this one will give us a negative deflection. So now how does the ECG represent a negative deflection? This one here is going to be a negative. This one here is going to be a negative. It's going to be a negative deflection. So now this one on the ECG, whenever you see a downward deflection, it represents a negative. It represents a negative deflection. Okay, it represents a negative deflection. Okay. Now we are going to be now repeating an experiment with this kind of the tissue, which is going to be a bit slightly thicker. Okay, this tissue is going to be slightly a bit thicker. It is too big compared to this tissue B and then tissue A. We want to see how is it going to be different in terms of what we call vector formation. Now, this tissue is going to be, for example, at rest. And whenever this tissue is at rest, it is going to be, the cells are going to be electrically negative. Okay. Now, let us pretend for a minute and we are going to be stimulating this tissue from this side. If you stimulate the whole of this tissue, these cells are going to start now accumulating a lot of the sodium. And once they accumulate a lot of the sodium, the resting membrane potential will move to the threshold. Once it reaches the threshold, voltage-gated sodium channels are going to be opening and a lot of the sodium will rush in, okay, and will make the electronegativity of the cells to be washed away. And these cells are going to become depolarized. And once they become depolarized, now the depolarization is going to be starting from this side, moving to the other side. Okay, so now we are saying that the depolarization is moving from the negative electrode going to what we call to the positive. Going to what we call to the positive electrode. Now, when you look on the depolarization of this tissue and the depolarization of this tissue, you realize that here we are going to be having a depolarization which is going to be a bit of a bigger magnitude. Okay, the depolarization generated in this tissue is going to be of a bigger magnitude compared to the tissue B and then compared to tissue A. What does this one mean? It means even the vector which is going to be created, is going to be of bigger amplitude. Okay, so now a vector is going to be of bigger amplitude. Okay, and this depolarization and this vector is going to be carrying what we call the depolarization, which is the flow of the positive charge. Now, if we bring in the rules of what we call the galvanometer, whenever the positive charges or the depolarization moves away from the negative electrode towards a positive electrode. We said that one is going to be giving us a positive deflection. But this time around, the positive deflection is going to be having an extensive, big kind of the amplitude compared to the experiment of the tissue A and then what you call tissue B. What do I mean by this? This is going to be now the size of the amplitude of this positive deflection. It's going to be giving us this kind of deflection. Now, when you see this deflection, this positive deflection, and this kind of positive deflection, you realize there are going to be a difference. And the difference in this one is going to be as a result of what we call the thickness of the myocardium. If the myocardium becomes thick, even is going to be giving us a lot of the depolarization, which will give us a bigger vector, which will also give us a strong kind of the positive or the negative deflections. Okay, so now that one also makes a lot of sense. Now, if this tissue becomes fully depolarized, there is not going to be any kind of electromagnetic force which is going to be generated if it is fully depolarized. For that reason, it's going to be the pointer is going to be now coming back to what we call to the neutral position. And whenever the pointer moves back to the neutral position, this one gives us what we call an isoelectric line. Okay, and even also whenever the electrical impulses are moving perpendicular, okay, whenever they are moving perpendicular on this kind of this tissue, also that one, the pointer is going to be also moving back to the neutral, which will also give what we call an isoelectric line. And even again, another reason why we may even have what we call isoelectric line is like, for example, on AV node. The AV node also holds the action potentials for approximately 0.1 second. That one also can also produce us what we call an isoelectric line. Okay. So now, the whole of this kind of the myocardium is fully depolarized. So now let's now first pretend that now it's time to repolarize. Now, how is repolarization going to be happening? First of all, repolarization means the cells are going to be now allowing the out movement of what we call the potassium. We are going to be having efflux of what we call potassium whenever the cell is becoming repolarized. So now let's first pretend for a minute that this kind of the tissue is going to be getting repolarized from this side. Okay, it's going to be getting repolarized from this side, going this side. And we have said that whenever this tissue is getting repolarized, it means it's going to be now starting to regain its electrical negativity just because of the exit of what we call the potassium. So now the electrical positivity is going to be getting lost as these cells are going to be becoming electrically negative. Okay. So now they are regaining what we call its electrical negativity. So now, when this tissue regains its electrical negativity, we say this tissue is getting repolarized. But the repolarization was moving from this side going this side. It means even also the vector which is going to be created is going to be facing this side. Okay, it's going to be facing this side. But this time around, this vector which is created is going to be as a result of what you call repolarization. Now, whenever the negative charges are moving away from the positive electrode towards a negative electrode, the principle of the galvanometer says that one also gives us what we call a positive deflection. Okay, whenever negative ions are moving towards a negative electrode, it gives us a positive deflection. And even also, whenever positive charges are moving towards a positive electrode, it also gives us a positive deflection. That is according to the principles of the galvanometer. Okay, we're going to just have a very quick break. Immediately after the break, we shall go through what we call the leads, because the ECG has 12 leads. Let's meet immediately after the break. Welcome back from the break. We are continuing with this session where we are looking on what we call the leads, because we said that the ECG machine uses approximately around 12 leads. Now, we need to first understand what is a lead, because it's something which is super very important. Now, a lead is going to be the different directions of the view of the heart's electrical activities. Okay, the different views of the heart's electrical activities. Now, I want to first pretend for a minute and say, for example, a lead to be like a camera. Okay, and we are going to be having 12 cameras that are going to be looking at the heart from different angles. Okay, so now these kind of the cameras are going to be our leads. They are going to be looking at the heart from 12 different angles, and all these cameras will be recording an image which can be seen on what we call on the ECG paper. Okay, let's pretend for a minute that this is going to be our heart, but now we're going to be putting cameras from different angles. Now, when you come over here, we have three categories of the leads. What are these three categories of the leads? We have those leads which we call the chest leads. We have what we call the chest, we have what we call the chest leads. When we talk about the chest leads, these are the leads which are going to be looking at the heart in a horizontal plane, okay? In that kind of the transverse horizontal plane. They are going to be looking at the heart, from example, from the right ventricular myocardium. They are looking at the heart also direct from what we call the interventricular septum. They also be looking on the anterior portion of what we call the left ventricle, and even also they'll be looking at it on the lateral sides of what we call of the left ventricle. Okay, and these leads are what we call the chest leads. These leads are the one which are going to be illustrated as you are seeing here. So now there are going to be 6 of them. Okay, the first one is going to be this one which we are calling the V1, which is going to be put on the right side of what we call the sternum, and then this one is going to be our V2, which is put on the left side of what we call the sternum. This one here is going to be what we call the V3, and then this one here is going to be our V4. This one here is going to be our V5, and then this one here is going to be our V6. Okay, so now these kind of the leads are going to be looking at the heart in a horizontal kind of the plane. Okay, so now you're going to be having a V1, you're going to be having V2, you're going to be having V3, you're going to be having V4, you're going to be having V5, you're going to be having V6. Okay, so far we have seen that we have already the 6 chest leads, which we call the precordial leads. Okay, then we also have some other leads that was invented by one of the great scientists, named as the father of electrocardiography, called William Einthoven. William Einthoven came up with a specific kind of a beautiful kind of a triangle that is going to be giving us more of what we call over the leads. You see this kind of this triangle. This man called William Einthoven, he placed electrodes on what we call the right arm, and then also on what we call the left arm, and even also on the left leg. And then he came up with this kind of this triangle. And this triangle is helping us to give us a view of different kind of the leads. So now this kind of the triangle is also going to be helping us in developing more of the leads that are also going to be looking at the heart from the inferior view. Okay, so now like for example, this kind of the positive electrode which is put on the left arm, we are going to be looking on what we call from the left arm, and then we look on this kind of on what you call on the right arm. So now for example, if I come and I look on the heart from this corner like this, and now this kind of the lead here, this one he called it as lead 1. He called it as lead 1. Okay, and then also there is another lead whereby we're going to be looking at the heart from the inferior view. Okay, we're going to be looking from what we call from the left leg, and then we look on what we call the right arm. So now we are looking at the heart from this kind of the view. Okay, so now whenever you're looking at the heart from this kind from the left leg and on to what we call to the right arm, he called this one as lead 2. Okay, he called this one as lead 2. And even also, you can also have this kind of a lead whereby we are looking at the heart from the down area, and we are looking on what we call the left arm. And he called this one as lead 3. Now, over the sudden, he came up with what we call Einthoven's law. And now, how does Einthoven's law say? He came up with what we call Einthoven's law. He said that when you add up lead 1 and lead 3, you will come up with lead 2. Okay, meaning that if you add lead 1 plus lead 3, you're going to be getting lead 2. That's what we call the Einthoven's law. Then we also have some other kind of the leads which are going to be also helping us in looking at the heart from different angles. We have this kind of this lead here, which is going to be looking at the heart from the left arm. And this one here is just called AVL. Okay. We also have another kind of the view which is going to be looking at the heart from the right arm, and this one is what we call the AVR. And even also we also have another kind of the lead which is going to be looking down on what we call on the left foot. Okay. So now this one here is what we call AVF, is looking from the heart directly from what we call from the left foot. Okay. So now when you look at this, we have now also created more kind of the six leads. What are these six leads? We have these ones which are called augmented leads. Okay, we have these ones which are called augmented leads. And when we talk of augmented leads, we are going to be having AVR, we're going to be having AVL, and also going to be having what we call AVF. Okay, and these kind of the leads, they are going to be unipolar. Okay, they are going to be what we call unipolar. And then also these kind of the leads, lead one, lead two, and lead three, these ones are going to be what we call the bipolar leads. Okay, so now we have also another category of the leads which we are calling, this was category number one, this is category number two, then also have category number three which we call the bipolar leads. The bipolar leads. And when we talk of the bipolar leads, you're going to be having lead one, you're going to be having lead two, and you're going to be having lead three. So if you have these three leads plus these three leads plus these six leads, you're going to be coming up with 12 leads, which is going to be a normal 12 lead ECG machine. Okay. Now, we have said that we are looking at the heart from different angles, and we have said that all these leads are going to be giving us a clear picture on the ECG machine. And now the question is, out of these 12 leads, which one of these leads is going to be giving us a clear wave pattern on the ECG machine that is going to be much of reference in this interpretation of what we call the ECG? When you look on these kind of the leads, they are all going to be giving us different kind of the views on our ECG machine. But the best kind of the lead that gives the clear wave pattern on the ECG for a normal human being is going to be the lead 2. Now look at this. This is going to be our lead 2. This is going to be our lead 2. We are looking from the left leg, and then we are looking to the what we call to the right arm. Now when you look on the structure of the heart, it is always trying to bend towards facing what we call the right side. Now it means that I'm going to be looking at the heart from this area like this up to what we go to the right arm. So now this kind of the lead is what we call the lead 2, and it's going to be giving us a clear wave format because you are looking at the heart from the inferior view. Okay, so now we are going to be using lead 2, which gives a clear waveform pattern of the ECG machine. Okay, and how is it going to be arranged? We have what we call a negative electrode, which is put on the right arm, and then also have what we call a positive electrode, which is put on what we call the left arm. And that kind of the axis gives us what we call the lead 2, which gives us the best clear wave pattern on the ECG machine. Okay. Now that we have had the clear orientation of what we call the leads, we are going to first have a very brief break. Then immediately after the break, we are going to be using this lead 2 and see how we are going to be how it's going to be helping us to generate our wave pattern, because this kind of the lead is going to be giving us a very good kind of the picture of the P wave. It will give us a very good picture of what we call the QRS wave complex, and also it will give us a very good picture of what we call the T wave. We are going to be putting our negative electrode on the right arm, and then also shall put a positive electrode on the left leg. And then we are going to be seeing how the electrical activities of the heart are going to be helping us in generating that wave pattern on what we call on the ECG paper. Okay, we meet immediately after the break. Welcome back from that kind of the short break. We are continuing with this session where we are going to be looking on the ECG waves, especially being recorded on what we call using the lead 2, because we said lead 2 gives us a clear wave pattern on the ECG paper. So now this one here is going to be now my ECG paper, okay, where our wave pattern is going to be drawn. And then this one is going to be now our lead 2. We said that our positive electrode is going to be put on the left leg, and our negative electrode is going to be put on what we call the right arm. So now this kind of the lead is going to be looking at the heart on the inferior kind of the view. You're going to be looking at the heart on this kind of the view, which is our lead 2. Okay, and we said that lead 2 gives us a clear wave pattern on the ECG paper on a normal human being. Okay, so let's go ahead and get started. So now we want to be measuring the electrical activities, how they are going to be moving throughout the heart, and then how they are going to be illustrated on our ECG paper. Now, we said that the heart has that intrinsic ability to spontaneously depolarize, sending those kind of reaction potentials down the entire myocardium, causing what we call contraction on its own without any external effect. And that one is what we termed as the automaticity. And we said who was generating the automaticity? It was the SA node. And where is the SA node located? The SA node is going to be located on the right atrium, preferably on the entrance of what we call the superior vena cava. That's where we're going to be having our sinoatrial node. Now, throughout the entire of this study, you should be remembering the following terminologies as we looked at in the previous video. We need to remember what a vector is. We need to remember what is a positive deflection. We need to remember what is a negative deflection. And we also need to remember what is an isoelectric line. Because you're going to be using those kind of terminologies during the study of what we call the wave formation on our ECG paper. Okay, so let's go ahead and get started. So now, we want first pretend for a minute that now our SA node is going to be now firing. When it fires, it's going to be now spreading those kind of the action potentials. And those kind of the action potentials are going to be now spreading on what we call the left atrium and what we call the right atrium. And we said that on the left atrium is going to be through what we call the Backerman's bundle, and then on the right atrium is going to be what we call the internodal pathways. Now the question is, this kind of the depolarization is going to be moving from the SA node, moving towards what we call the left atrium, and even also moving towards what we call the right atrium. Now, this kind of the depolarization, we want to be looking at its direction, where it's going to be pointing, and this one will also help us to generate what we call a vector. Now, when you see the SA node and it fires, this kind of the action potential, this kind of the depolarization is going to be moving in this kind of the way. So now, if I can create my vector here, this is going to be the direction of my vector. Okay, this is going to be the direction of my vector. Okay, now when you see on the direction of this vector, you are realizing that the depolarization is moving away from the negative electrode and it is facing towards the positive electrode. So now, what does the principle of the galvanometer say? It says that whenever the positive charges or whenever the depolarization is moving away from a negative electrode towards a positive electrode, that kind of the deflection is going to be a positive deflection. So now our ECG machine is going to be having what we call a positive, deflection. Okay, so now this kind of deflection here is what we call our P wave, and this P wave is going to be denoting what we call atrial depolarization. It is such another beautiful thing. Okay, now when the depolarization spreads throughout the entire kind of the atrium, they're also going to be causing them to contract to push the blood down. Now, this kind of depolarization, it does not cross from the left atrium down to the ventricles on these sides. Okay, it has, some of them are going to be dying out on these corners, but some majority are going to be converging, and then they come on this specific type of the nodal cell, which we call the atrioventricular node. Now, this atrioventricular node is a slow conductor. What do I mean by this? He has the potential to hold this kind of the depolarization, this kind of the action potentials for approximately 0.1 second. It can delay these kind of reaction potentials for approximately 0.1 second. The fact that this AV node is holding this kind of depolarization for approximately 0.1 second, it means there is not going to be any kind of the movement of the action potentials within this time. Now, if there is not any kind of the movement of the action potentials because they have been held by what you call the AV node, will there be any kind of the deflection to be noted on our ECG paper? There is not going to be any kind of reflection, and for that reason, our pointer is going to be coming back, to the neutral, and then to have this kind of isoelectric line. Now, this kind of the isoelectric line, it notes that this is the small period during which the action potentials are held on what we call the AV node. Okay? Now, our AV node is now going to be allowing the movement of what we call the action potentials. Now, when it allows what we call the action potential to cross down to what we call to the myocardium, first of all, it's going to be moving through what we call the bundle of his, from where the bundle of his are going to be now splitting into two. It's going splitting into what we call the left bundle branch and what we call the right bundle branch. All of them are going to be inside what we call the interventricular septum. Now, the question is, of these two right and then left bundle branches, which one is going to be depolarizing the interventricular septum? The answer is the left bundle branch is the one responsible for the depolarization of what we call the interventricular septum. It is such another beautiful thing. So now the question is, what is the direction of the depolarization coming from what we call the left bundle branch to depolarize the entire kind of interventricular septum? The direction of what you call the depolarization is going to be in this kind of the direction. Okay, it's going to be in this kind of the direction. So now, if I can make a mean vector for this, is going to be like this. Okay, it's going to be like this. So now, when you see how the left bundle branch is going to be depolarizing the entire kind of the interventricular myocardium, this kind of the depolarization is going to be now moving towards what we call the negative electrode. It is moving away from the positive electrode and is moving towards what we call a negative electrode. Now, by the principle of the galvanometer, whenever positive charges move from the positive electrode towards a negative electrode, that one gives us a negative deflection. Okay? So now our ECG machine is going to be having what we call a negative deflection. Okay? So now this negative deflection is what we call our Q wave. Okay? So now we said that this one here is going to be our P wave. So now this one here is going to be our Q wave. Okay? Now that the whole entire interventricular septum is fully depolarized, now this kind of depolarization is now going to be moving down to what we call to the ventricles. Now the question is, how is the ventricles going to be getting depolarized? These kind of the Purkinje fibers are going to be deeply buried, more especially on what we call the deeper layers of what we call of the myocardium. Now, this kind of depolarization on what you call ventricles is going to be starting from the inner part going outwards. That's going to be the normal kind of the direction of what we call the depolarization. How is it going to be happening? This kind of depolarization is going to be moving in this kind of the manner. Okay, in this kind of the manner. Okay, you see how the depolarization is going to be moving. Okay, it's going to be moving like this. Of course, when we talk of depolarization, we are denoting the movement of the positive charges. So now it's going to be moving from inside going outwards. So now, if I can create a vector for the case of what we call the left ventricle, we said that the thickness of the myocardium determines the size of the vector, meaning that the vector which is going to be produced by the left ventricle is not going to be the same as the vector produced by what we call the right ventricle. So now, if this is going to be the vector, of what we call the left ventricle, this one here is going to be slightly a bit smaller. Okay, it's going to be slightly a bit smaller because the thickness of the myocardium on the right ventricle is going to be smaller compared to what we call the left ventricle. So now, if I can get a mean kind of the vector, I combine all these kind of the vector, I'm going to be getting this kind of the vector, which is going to be like this. Okay, which is going to be like this. Now, this vector is going to be a bit bigger. Okay, and the fact that it's a bit bigger and is facing from negative electrode, it is facing towards a positive electrode. And by the principle of the galvanometer, our kind of the pointer is going to be giving us a positive deflection. By the fact that this kind of the amplitude of what you call this kind of the vector is going to be a bit strong, for that reason, you are going to be having a very strong kind of the deflection upwards. Okay, so now this kind of the strong kind of the amplitude of deflection denotes that the vector which was created was a bit stronger compared to other kind of the vectors which have been forming. So now this kind of the wave which has been formed, this wave here is what we call our R wave. Okay. Now, the question is, we have now depolarized what you call the apex of what you call the right and then the left ventricle. We have not yet depolarized what you call the base of the ventricles. We also need to depolarize the base of the ventricles because they are going to be depolarizing last. So now, how is depolarization going to be happening on what you call the base of the ventricles? These are going to be the base of the ventricles. Okay, these are going to be the base of the ventricles. Now, what is very, very much funny is that the depolarization of the base of the ventricles is going to be somehow a bit unique. The depolarization is going to be moving from out going in. Okay, from out a bit going in. So now this is how the depolarization is going to be moving. Okay, the depolarization is going to be moving like this. So now, this kind of the depolarization is going to be trying to face in this kind of the direction. Okay, it's going to be facing a bit in this kind of the direction. Now, this kind of the direction is going to be moving away from the positive electrode and is trying to move a bit towards the negative electrode. And by the principle of the galvanometer, whenever positive charges move away from the positive electrode towards a negative electrode, what's going to be the direction of the deflection? This is going to be giving us a negative deflection. For that reason, the depolarization of the basal areas of the ventricles are giving us a negative deflection. For that reason, you're going to be having what we call a negative deflection. Okay, and this negative deflection is as a result of what we call depolarization of the base of the ventricles. Okay, and this kind of the wave is what we call our AC wave. Okay, it is such another beautiful thing. So now we have now fully depolarized the entire ventricular myocardium. In the previous video, we said that whenever a piece of the myocardium is fully depolarized, our deflection pointer comes back to the neutral. Now, the same is going to be happening here. Now, our entire ventricular myocardium is fully depolarized. Shall we have any change in the membrane potential? At this time, the whole of this area is positively charged. For that reason, our pointer is going to be coming back on what we call to the neutral position. So now our pointer is going to be coming back to the neutral position and it's going to be giving us this kind of isoelectric line. And this kind of the isoelectric line is denoting that the entire ventricular myocardium is now fully depolarized. Okay? Now that we have seen that the whole depolarization process has taken place, now the heart is going to be now contracting and it pushes the blood off the ventricle. But of course, a contraction wave is going to be followed by a relaxation phase. And the relaxation phase is going to be now a repolarization phase. Okay? So now we're going to be having what we call ventricular repolarization. So now we said that repolarization means that now the cells are going to be now losing potassium ions. And whenever they are losing potassium ions, they are now starting to regain their electronegativity. Okay? So now, what's going to be happening? Here is what's going to be happening on what you call the repolarization of what you call the ventricular myocardium. The areas that got depolarized the last, it is the area which is going to be starting in the process of repolarization. We said that depolarization was moving from in going out. It means that the outer areas of the ventricular myocardium was depolarizing last. This is the area which is going to be repolarizing fast. Okay, this is going to be the area which is going to be repolarizing first, meaning that our repolarization is going to be starting from this side. So now we're going to be now, and the repolarization is going to be aiming at washing positive charges. Okay, so now it's going to be moving in this way. So now even also this area also gets repolarized. Okay, and even also this one also gets repolarized. Okay, so now this process is now going to be happening throughout the entire ventricular myocardium. Now when you see the movement of this kind of the repolarization, is going to be moving from the outer areas of ventricular myocardium, moving in that kind of the direction. So now this is going to be now the direction of what we call the repolarization process. So now if I can create a vector, here, it means our vector of repolarization is going to be facing that side. And to be even more specific, this is going to be a repolarization vector. And even also this kind of the ventricular myocardium on the right side is also going to be repolarization like this. Okay. Now when you see this direction of the repolarization, it is moving from the outer areas of the ventricular myocardium and is facing towards what you call a negative electrode, meaning that the negative ions are moving from a positive electrode and they are facing towards what you call a negative electrode. By the principle of the galvanometer, it says that whenever negative ions are moving from a positive electrode towards a negative electrode, it also gives us a positive deflection. And even also, whenever positive charges are moving towards the positive electrode, it also gives us a positive deflection. So now our pointer is going to be giving us a positive, okay, a positive, and this positive is going to be our T wave. And this T wave is going to be denoting what we call ventricular repolarization, because the ventricles are now coming back to the relaxation phase. Okay. So now, to finish it all, we are going to be now making a very quick summary of the meaning of all these waves. We said that this kind of the P wave is going to be denoting what we call atrial, bipolar, what we call atrial depolarization. Okay, the atrium are depolarizing. Now, we said that this Q wave was following what you call septal depolarization. Okay, so now our Q wave was denoting what we call septal depolarization. Okay, such a beautiful thing. So now from the Q wave, we moved to what we call to the R wave. And this R wave was denoting major ventricular depolarization. The bigger parts of what you call of the ventricles, we are getting depolarized. So now this kind of the R wave was denoting major ventricular, depolar, depolarization. Okay, major ventricular depolarization. Okay, and then we moved to what we call to the S wave. Okay, when we moved to the S wave, we said that this one was mainly focusing on what we call basal ventricular depolarization, the base of what we call of the ventricles. Okay, so now this one was mainly focusing on what we call ventricular ventricular depolarization, depolarization. And then lastly, when we see on the T wave, when you look on the T wave, this T wave is going to be denoting what we call ventricular repolarization. Okay, it's going to be denoting what we call ventricular repolarization. Okay, it's denoting what we call ventricular repolarization. And of course, when you see this QRS, it makes what we call a complex. Okay, and this complex of the QRS denotes mainly what we call ventricular depolarization. You may be finding very many books writing it as QRS complex. Okay, QRS complex. This one is going to be denoting mainly what we call ventricular depolar, depolarization. Okay. Thank you very much for watching. And if you think whatever I've talked is making sense, is really adding to your benefiting, please, you can hit the like button, comment down in the comment section, and please subscribe. As always, Tumnad, until we meet next time.